Today is the 29th July 2026. I'm doing another practice of trying to execute on the plan that I did yesterday. I want to look into, again, this drawing freeform format. I'm trying out how it feels if I'm more so preparing kind of the drawing and not more I've prepared more the structure of what I want to draw, what I want to visualize, than what I want to talk about in a little bit more detail, and want to see how that feels executing on that, and how that helps me with the drawing, connecting with talking, and how it helps me maybe with synchronizing how I can talk and how I can visualize it at the same time, how that feels. I just want to look at this. So the topic of today is why a voxel engine is so much fun for me. And to begin with, I think voxel engines are for me very fun because they're just so simple, and also it's just a very abstract and pure informational problem, but it creates a lot of limits that one have to work around, and I just find it very intriguing. So let's just start with looking at, well, what's a voxel engine at its core? Why are voxel engines at its core on informational side so simple? So what is a voxel engine? A voxel engine is basically kind of a program or library in most of the cases that allow me to work with voxel data. What is a voxel? Voxel is a volumetric pixel. Voxel stands, as we have it, the Vox is for, or the VO is for volumetric. This is the volume writing, and the Excel is for the pixel. So it is voxel. This is where the name comes from, and that's also what it is. So pixel, if you look at pixels are, we just have a grid. In pixels, with a pixel we make an image based out of a grid. So we just have a grid of pixels, and the information there then is that we just put some kind of color into these lots. So we just can colorize the pixels by putting different colors in like the pixel slot. So this is a pixel, this is a pixel, this is a pixel, and by making a grid of color pixels, we have an image. And voxel is just that, just in 3D. So we just have a three-dimensional grid. So we don't just have one layer, but, well, let's say we have a grid of 16 by 16 voxels. This would be an image. For voxel we have a three dimensions. We just add a set layer. So we have here the X layer. This is X. This would be Y. And in voxel we then have additional layers, like here, like on top of this, which would be the set layer. So we just have additional, so this would be set 0. And we would have an additional one that would be one with a complete new voxel data in it. That's kind of on the base what a voxel is. And there are a lot of ways, of course, to do the individual voxel. Currently, with my current voxel engine, I'm actually doing exactly this. I'm actually doing color-based voxels. And then there's not a lot more. So voxel engines are just grids of data. The data can be very different. Like you can have a voxel, if you look just like at a single, we just look at a single voxel. How can we represent it? Well, we could just use a color. So we could just have an RGB, an RG and B color, or maybe even an alpha. Let's just do. I mean, in my current voxel engine, I'm actually doing RGBA, and for one we would do a byte. So 1 byte per color value. That would be, each color would then have a value from 0. Whoop, that was too much. Come on. No, okay. I can't, too stupid to do undo. Wait. Each value would have a range from 0 to 255. So we have, each color value can have 256 different states if we do RGBA. We of course could do an indexed kind of voxel, so we could just have either 1 byte or 2 byte voxels. So in 1 byte again we just have the 256 states of voxel, and we could say, okay, we just have 256 and we just make kind of a color palette. So we could just like define a palette where we just say, I don't know, 0 is like, where do we have it? So 0 is like green, and we have like this one, and we make like a red. So I mean 0, it probably wouldn't be 0, it would be 1 and 2 and 3, and I by default say like the 0 voxel is just an empty one, and so you would just write the grid of voxels by just writing the byte information of like the voxel palette or the color palette into the voxel, and then just use that to do later on some meshing and stuff like this, and how you want to display it. And you would just use them as types. You would just use the byte information of a voxel for like 16 bits, 256 types, and you would just do the types. You can of course also go like with 2 bytes. This would be 16 bit, like a short or a U short in many programming languages, which would give us 65,536 different states, which for many cases that's like more different types of voxels that you can need. Of course, we can also just not do RGBA and just do a whole 4 bytes, so a 32-bit voxel, which would give us 4,294,967,296 states. So 4 billion voxels, which is, or not voxels, but different types of voxels, which is kind of insane. But that is kind of the base of how a voxel engine data-wise would work. We just have a grid of voxels. What a voxel means depends on the engine. I currently use a 32-bit voxel type. I just use a RGBA for my voxels right now. I have done it with different types, like index-based, as I just said, with the voxel palette. And from that there comes like where voxel engines are very easy. So where are the issues with that? So just have a 3D grid that you operate on. So you just do operations on the 3D grid, which in programming the easiest way is to just use 3D arrays, which have its issue on its own. Like if you have a 3D array, you have an array. So you have like a more of like a table. We just have, as we had before, the x, the y, and then of course you would have a z-axis with like different tables on top of it. Kind of. You could also, I'm mostly doing flat arrays if I'm using arrays. So you would pack this array here. So you have like, this is 1, this is 0, 1, 2, 3, 4, 5, 6, 7, 7, 8, 9, 10, 11, and then you would have 12 would be the x0, the y0, so this field, and the 1 on this axis would be the 12 field. So we would then flip up to the z axis, and this would be 12. So if we pack this in a linear array, not in a three-dimensional array, but in a linear one, you just have the voxels each after another, and it just goes linearly, and you just then have to map how that maps onto the axis by its own. And well, then you cannot not just do arrays, which arrays are very efficient when it comes to iterating over them. You can do sparse trees and quad trees to just compromise like the memory that you use, but I want to get into that a little bit later on. Let's look at where does actually the issue come from. Well, like it's very simple. Voxel engines are very simple in the way that well, you just have very simple data and you just operate, and then you just do operations with, well, a grid of voxel data, whatever the format of the voxel looks like. So let's make it very simple. But okay, if it's so simple, why it's actually interesting? Well, it's interesting because with voxel you have a scaling issue. The issues with voxels mostly come with scaling. Why? Well, if we just look at a very small voxel chunk, or just very small voxel data, we have like, let's just say a 16 by 16 by 16 voxel area, which are not that many voxels. But if you make this, you actually have 4069 voxels. If you go up, for example, I often use a voxel size of 2 centimeters. With 2 centimeters, that means that 1 square or 1 cubic meter has 50 by 50 by 50 voxels, which would be 125,000 voxels, which are already a lot. Now, this is like the voxel amount, so depending on what your format is for voxels, so if you use a 1 byte voxel or a 2 byte or a 4 byte voxel, you basically have to multiply all of them just from the memory side. So with a 4 byte voxels, you have to do this times 4 on this times 4, which here would be 500,000 kilobytes already. Not 500,000 bytes, so it would be already 500 kilobytes just on memory size, just to store the voxels in RAM, which, I mean, at this point is not much, but a cubic meter in voxels for a whole world is also not that much if we think about it. If we go just up by like 5 cubic meters, which is not that much space in like a game world, we would have an area of 250 by 250 by 250 voxels, which already would be 256. Where am I? Sorry, no, I was looking at the wrong thing. This would be already 15,625,000 voxels in just 5 cubic meters, which is not that much of like a volume. For, I mean, very small voxels it is, but 50 million voxel, again, just for storage size, this would be times 4. So with 15 millions times 4, you are at 60 million. So this would be 60 megabytes and data, which starts to be quite something, which again are just 5 cubic meters, which is not that much of a space like in a game. So you can easily see scaling, these things scale. And of course, when we have 15 million voxels, that means if we want to operate on such voxel data, we have to do 15 million operations just to operate on a 5 cubic volume. So we have an insane amount of scaling with voxels very quickly, and that can actually very, very quickly push even modern systems to their processing limits. And so so voxels very quickly give us create a very simple in what they are and how they work. But out of this simplicity and out of its limitations, there then come a lot of very interesting, how I think about it, very interesting scaling issues. So we have, for example, can look at performance-wise. We have like the CPU on one side, we have the CPU. On another side, we have the GPU. This is the GPU, and on another side, we have the memory, so just the RAM. And we can put them in a triangle. And pretty much when it comes to optimization in general on a computer, when we have something that is very CPU intensive, and we want to have it to be less CPU intensive, that means we have to move it from the CPU side to somewhere else. So In the simplest way, that means we have to move it towards RAM, so to use more memory and do some kind of caching. So we don't calculate everything on the fly in the CPU, but we cache something. But that means, well, memory size has to go up, or we can pull it to the CPU so that we don't use the performance on the CPU side, which means, well, now the GPU has to do much work, which might not be what we want. If we have a game, for example, that use a very complicated rendering things, we might not want to put more load onto the GPU. Maybe that's what we want. It very much depends then on the context. And here we just see just from, well, how it pretty much always works, we very much come to a limit where maybe we can't do 50 million operations every frame on the CPU, so we have to move it somewhere else. Do we want to move it in RAM? Then how much RAM do we have to operate with? Can we run out of that quickly? Potentially we can. Would we want to optimize? If we optimize use less RAM, well, we have to use more CPU or more GPU. So it's very much this triangle where, well, if we want to be here, so you very much have to choose. So it makes very interesting choices of what do we want to do and what kind of side do we prefer, where it's for us more important on what the requirements are. And then it's not just the thing of, okay, they're not ideal ways to structure, because where they deform it, and how do we use arrays? Do we use some kind of sparse trees or something like this, or like quad trees for like our voxel structures which optimize the RAM side? What kind of algorithms do we use on the CPU side, or do we want to put it onto the GPUs a lot? Which then also makes it a little bit, if we do things on the GPU, we kind of limit ourselves in how we can communicate between this, like this becomes the bottleneck. And CPU-GPU communication is a little bit difficult. Again, if we want to limit ourselves to CPU, we very quickly run into performance issues. If we want to optimize this, we can put it through the memory, which, well, then it depends, okay, how much memory, like minimum system requirements we want for the Voxel engine, which for me just very quickly we just ran into like the performance issues of a system, and like working with that makes it very interesting. And there's not an optimal Voxel engine, because it all depends on, well, for what is it for, depending on like where one wants to use a Voxel engine and for what purpose. We have different requirements on, do we need more, or what are like the bottlenecks? Do we have a program that everywhere else needs a lot more GPU, or do we have very strict memory limits, or like what is the strong and the weak side of a system? What is the use case? What else do we need around it? And what kind of system resources will they need? And according to that, a different approach to a Voxel engine is needed, which makes it very interesting. So just by the scaling issue of Voxel engine, we very quickly ran into, depending on the context where and how we want to use a Voxel engine, we need to optimize them according to memory, CPU and GPU, which I just find very interesting. Then, well, in the next step, Voxel engines make it very interesting in different areas. Like if we just look more so, like for example, on the graphics side, if we just look at Voxel engines from a graphical perspective, Voxel engines can allow us, if we do more customized rendering with a voxel-based world, allow us to have a lot of optimization on the graphics side, because we know the structure of a world and we can use the grid structure of voxel data to have highly performative tricks that we can use in rendering. I mostly don't go this route, because mostly I don't use with world grids for voxels, but like in games like Minecraft and things of that kind of world, you can do really smart and clever optimization tricks based on the voxel structure for graphics and for rendering, which I find is like really interesting, a very interesting area to do, where voxel engines can expand to. Then you have more of the like physics side of the physics side from voxel engines, which I think physics with voxel is quite difficult. I mostly do voxel engines like in engines like Unity, or currently I'm working in Godot. There, well, for in Godot it would be the Jolt physics engine, And using like a pre-made physics engine like Jolt or like Physics or like I think it's Bullet 3D, another physics engine open source one. Using voxels in that kind of sense can be quite difficult, especially doing it dynamic, because changing voxel shapes or changing physics shapes dynamically can have a huge performance impact. So working around that creates new kind of limitations and challenges to overcome. Maybe in the future, which would be very interesting, would be a custom voxel-based physics engine, like writing a complete 3D physics engine from scratch just for voxel engines. Would be a very interesting project and a time to do, and would be a way to expand. And I think even there you would have actually advantages over having a customized voxel-based physics engine over trying to do voxel physics and dynamic, like voxel destruction and manipulation and changing physics shapes in like an engine like Jolt or any kind of pre-made physics engine. Then you, of course, like one of the biggest areas before we even get to them, if you're not doing any kind of voxel-based rendering, which mostly we don't do because our GPUs are based for rasterized rendering, we would do some kind of meshing. So a mesh is like points connected together to create a face. In this case, like the basic mesh is a triangle, and you would have to create a way to use like your voxel data, like your grid shapes, and to mesh them into triangles and into the surfaces that we could then render for our assets or for our world, or to export them and then use them in Blender, animate them, do whatever we want with them. That's like just voxel meshing if we do this like in a box style, or if we want to do more smooth voxels, we just mesh a volumetric data from marching cubes or any kind of more advanced voxel meshing algorithm. It's a very interesting area and very interesting problems and algorithms to solve and to tinker with. So that's an expanding just of the pure abstract and informational side of voxel grids. And then of course on top of that you have kind of you could do simulation of like voxel world. You could use voxel data to either do some kind of cellular simulation or other kind of simulation where just a very simple view of the data and of the world structure can help you to make more sophisticated simulation, which would be a lot more difficult with like normal kind of assets, like with normal meshes. With voxels, it can become a lot more simple, like destruction systems are a lot more simple to do with voxel systems, or any kind of like growing stuff, burning stuff down, these kind of things, doing them in a simulated way with voxels is an area where this very simple and pure informational form of voxel engines can expand into the graphic, the physics, the meshing and the simulation side. These are just the areas that I think a little bit with, and there are probably a lot more that one can do with voxel engines that are not used in many ways, but I find that they're just a very, again, simple and abstract problems that are very interesting to solve, and that just create very interesting and limiting challenges. That's just something that I really like to work on. And yeah, so that's why I enjoy voxel engines that much. This was not what I wanted to do. I messed this up. All right. I hope you have a nice day, and thank you for watching.